Okay, so multiplication of a vector by a scalar. Now a scalar is a number, okay? Essentially you could say with no direction. When we multiply scalars, we're looking at a term, and usually we represent a scalar by the letter k, okay? We'll call something like vector A. Let's say we have our vector here. That's our vector A, we'll call it. Okay, and we're going to find multiples of this vector. Okay, k can be many different numbers. In fact, we'll write a couple rules out for it. If k is greater than 0, it's the same direction. All of your favorite bands. That's nice, man. It's in the same direction. If k is less than 0, it's opposite direction. Okay. So what I mean by that is, first of all, we can change the length of it also. If, we'll also put in, so we'll call this our if, and if k is greater than 1, its length, or longer, we'll call it. We have a longer vector. And if k is between 0 and 1, we have a shorter vector. So we'll use those terms to describe this stuff. Nope. Page 1. It's a shorter vector. So what we mean by that is our A. This would be negative, obviously. This gives us our negative A. It's going in an opposite direction of the vector before. In this case, let's do this vector. So we're going to call this 2A. So it's roughly twice as large as the first one. We'll say that this is a vector A and that's a vector A. So 2A is essentially twice as long as vector A was in the first place. And let's say we had, I'll do my best to make this a half. This would be indicative of half of vector A. In other words, it's half as long as the original vector, which is vector A. We'll copy it here. Yeah, it's about right. No, it's not. I'll call that vector A. Okay. So that's what we're talking about in reference to. This is vector A. So that's our original vector A. 2A makes the vector twice as long. Half A makes the vector essentially half as long. And then you can change the direction by making either positive or negative. Positive keeps the same direction and lengthens it or shortens it. Negative does the same thing, lengthens or shortens it, but gives it the opposite direction as before. Okay? You can represent certain vectors by scalar multiples of other vectors. An example of this, we can use a Cartesian plane for. In fact, what they do in some questions is we'll look over this one. We'll look at example 2. So we'll skip over example 1. Example 2. It says vectors x and y are unit vectors. Now a unit vector means something has a magnitude of 1. So vector x and y are unit vectors. So, and a unit vector of 1. Okay? So x and y are unit vectors that make an angle of 30 degrees with each other. Okay? So we're going to just draw a picture. They're both unit vectors. We don't know what direction they're facing right now. We're just going to give them directions. We'll say that this is x. And we'll call the other one y. Here's our y, x, and they make an angle with each other of 30 degrees. Okay, so that's information they've given us in the question. Calculate the value of. Okay, so here's our first question. Absolute value of 2x minus y. So this goes into what we did the other day. So they want the absolute value of that. That's very important. The absolute value, they essentially just want the magnitude. We don't have to tell them what direction things are moving in because they're just talking about absolute value of something. So what happens here is like we're going to follow a story like we said before. 2x. Well, we have 1x here. What I'm going to do is make this twice as long. So what I can do here is copy. Scroll down. Let's make this story. Paste. Paste. So this is now, we've taken 2 of them. That's the equivalent of 2x. So say this is our starting point. This is 2x. Okay. And we know that our y still makes an angle of 30 degrees with everything. This is still an angle of 30 degrees. So let's see what we can do from there. And then wants negative 2y. So we follow our very first one. We go across 2x. And then from there we're going negative y. Well, infinite colonna. Let's do that. It's a little easier. I take this. This would be the positive y direction. Okay. But because it's negative y, we're no longer going that direction. We're not going upwards. We're going downwards. So we put the tail over here and go the other direction. So here's our new tail. Okay. So this is where we get to. And essentially you can represent this with a letter or with the new resultant vector. We'll call this, or we'll do it in blue. This is our new resultant vector, which is essentially, this vector here is 2x minus y. Okay. Now, because I actually have direction to my resultant vector, I'm not representing it as absolute value yet. But all they really want is the distance of that vector. Okay? So when we do the distance of that vector, we're going to try to figure out some stuff here. We know that it's 30 degrees, and we know the unit vectors are how far? And remember the magnitude of the unit vectors? 1. They're both 1. So we know that this has a magnitude of 1, and this has a magnitude of 1. Therefore, what's the magnitude of 2x? 2x is equal to 2. And the magnitude of negative y? What would it be? Yeah, you could say it's negative 1, which is right. But we only need the absolute value of it, right? So we can think of it like distances. This is 2 units. And this is essentially 1 unit. You're right, it is a negative because it's going the opposite direction. That's what the negative tells us. But because we just want to know the magnitude of something, just the absolute value, essentially y is equal to 1. We have that. So now with our triangle, let's recreate it quickly over here. We essentially have a triangle that looks relatively like this. Our measurements are 2 and 1. We need to find out this. We're going to call it our new resultant vector. So we'll call it r, vector r. What? Here's the tough part of the question. We know that this used to be our old y, right? It made an angle of 30 degrees over here. Can I use that information to find out anything else in here? Yeah? What can I find? Which corner? The one that I'm on? Yes, exactly. This is also 30 degrees. Okay. So, I'm trying to find this distance. This is not a right angle triangle, but I have a side, an angle between, and another side. Anyone know what rule we would use to solve this? To solve for r? Cosine law. Exactly right. We would use cosine law. Okay? Now, cosine law, I hope you guys remember it, is essentially c squared, and c is the side we're looking for, is equal to a squared plus b squared minus 2 times a times b times cos c. And that would be, this would be our c in this side, or we'll call it letter r since it's opposite of a resultant vector. So we're going to plug some things in to find this. C squared is our new r vector squared is equal to a squared. Well, a in this case we'll call this side a, or 2x in this case. 2x is the distance of 2 This can be our side B or our side Y, which is 1. So 2 squared plus 1 squared minus 2 times 1 times cos 30. Okay. So r squared is equal to 5 minus 4 cos 30. Anyone know cos 30 times negative 4? Get my calculator. What is it? Okay, 3.464. Perfect. So r squared is equal to 5. Subtract 3.464. So 5 subtract 3.464 gives us 1.563. And then, because we're finding just the resultant vector, not the squared version of it, we need to find the square root of this. So square root of that answer, 1.23 roughly, which is equal to 1.239, we'll say. So our resultant vector in this case is 1.239 in terms of magnitude. That is the absolute value of that vector. If I find out what the actual vector is, I'd actually have to find out its direction. And in this case, its direction is still this way. And then I could find out degrees. I could say that, oh, I could find out the next angle here to find that out. But in this case, we're just solving for magnitude, so we'll just leave it as that for now.